Well, hi everyone. Thank you for tuning in here. I'm going to give you guys a bit of a crash course on a new group today, which is called the alternating group, and it's very closely related to the symmetric group. And this is a group that is very important in group theory, and so it's something I want to introduce you to. I'm going to let you know now that this talk is very prerequisite heavy on cycle notation. So you need to make sure that you understand how cycle notation works and how you multiply cycles in the symmetric group, because we're going to be doing that basically all the way through this whole presentation. If you're not comfortable with that, I have another video that I previously recorded about cycle notation in the symmetric group, and you might want to watch that before you try to tackle this one here. Okay? So I'm going to just start off by writing out the group S4. Okay, this is a good example. It's a group of size 24. And I actually wrote out all 24 elements of the symmetric group on 4 letters right here. Starting with the identity element. Okay, and then in this first column, you notice that all of the cycles that you see here have length 2. So we have, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. By the way, of course I think everybody knows this already, but for example, 2, 3 is the same as 3, 2. It's the permutation that swaps 2 and 3, right, and fixes all of the other numbers in the set. In this case, it would fix 1 and it would fix 4, right? So I don't have to write the cycles that have the first number larger than the second number. Here I've listed them all with the first number smaller than the second number. Okay? In addition to those cycles of length 2, there's 3 more elements down here where I'm taking all 4 of the numbers 1 through 4 and writing them into 2 pairs as two cycles side by side. And these are disjoint cycles. Notice I don't have the same numbers in either of the 2 cycles. They're completely disjoint. And that means that they basically are simplified, right, in the cycle notation. So for example, this permutation right here just swaps 1 and 2 and also swaps 3 and 4. Okay? So that's what I've got here in the first column. Now in the middle column, I have all of the 3 cycles. Okay, so the first one here, 1, 2, 3, it just means 1 goes to 2, 2 goes to 3, 3 goes back to 1. That's what that permutation does, right? Actually, the inverse of that permutation is the very next one on the list, right? The inverse permutation sends, 1 back to 3, 3 back to 2, and 2 back to 1, right? So these 2 are both inverses of each other. The next 2 3 cycles are also inverses of each other. The next 2 are inverses of each other. And the next 2 are also inverses of each other, right? So these are all of the 3 cycles. There are 8 of them there. And finally, there are some cycles of length 4 in S4. I've listed all of them here. There are actually 6 of them. So 1, 2, 3, 4, for example. What would be the inverse of that one? The permutation that sends 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. Well, how do I undo that permutation? What would I have to follow that up with to get back to the identity element? Well, if 1 is going to go to 2, 2 to 3, 3 to 4, and 4 to 1, then the inverse function should send 1 back to 4, 4 back to 3, and 3 back to 2, and 2 back to 1. These 2 are inverses of each other in S4, right? And what about the inverse? So this guy is paired up with this guy. The cycle 1, 2, 4, 3, that sends 1 to 2, 2 to 4, 4 to 3, and 3 back to 1. So the inverse permutation would send 1 to 3, 3 to, so we go reverse, right? 1 back to 3, 3 back to 4, 4 back to 2, and 2 back to 1. That's actually this one, okay? And then by process of elimination, you can check that these 2 would be inverses of each other as well. In all of these cases, we've written down the cycle notation for the elements of S4. One of the advantages of that notation is that the order of the elements in this S4 group is just the LCM of the cycle lengths. Okay, you remember that? So if my cycles are disjoint, meaning that I don't see the same number in more than one cycle, right? So like down here, these are all disjoint cycles. Given that, then the order of any one of these elements is just the LCM of the cycle length. So all of these elements right here, right, have order 2. Just write that down. Order 2. Okay, everything in the middle column, right, is going to have order 3. And everything in this last column is going to have order 4. Okay, so those are the orders of those elements. Okay? All right. I want to make a quick observation here that this is a very nice way to write these elements, but there is a little fact that is useful, and sometimes we're going to be writing these elements in a different way. In fact, to describe the alternating group, it's going to help if I write some of these elements in a slightly different way. So the first thing I need to do is talk about a transposition. These cycles, these single cycles of length 2, are called transpositions, right? So a transposition is just a word. It's just a word that we use. A transposition is a cycle of length 2. So it's just going to look like that kind of a notation, right? It's just a cycle of length 2. So I've got some transpositions here. Here I have products of 2 disjoint transpositions. Okay, so we have that. But what's really nice about the idea of a transposition is the following little theorem, which is going to be very easy for me to explain. And it just says that every element, sigma, in the symmetric group. So anytime you have a symmetric group, and you take an element out of it, that sigma can be written. It can be written as a product of transpositions. Okay, so every sigma can be written as a product of transpositions. And the best way for me to justify that is to just sort of show you how to do it. So I'm going to just call this as a proof. I'm calling it a reason here. If you took an element, I don't know what it has for letters necessarily. Let's just imagine we have some cycle here. I'm just going to call it A, B, C, dot, 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 up to Z. Okay? I claim I can break that down as a product of transpositions. And the way that you would do that would be as AB times AC times, wait, do I have this right? No, I'm doing it backwards. Sorry. It's easy to get this backwards. It's going to be AZ times AY times dot, 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 dot times AC times AB. Notice that this is just a product of transpositions here. Notice that I did not say disjoint transpositions. These transpositions all share the letter A, don't they? It's not a unique representation, and it's not a disjoint representation, right? But just as practice with cycle notation, you could practice trying to multiply out the right-hand side from right to left and see what you get. So if I start at A, okay, let's just try this. If I start at A is going to get sent to B right here, okay? But then as I look to the left, I don't see any B's anywhere else later in that expression. So A is going to go to B. Okay? Now what if I start with B? Well, come over here. If I start with B, notice that B gets sent to A by that rightmost transposition. And then A ends up at C. And now there's no more C's to the right of that, which means that C gets fixed the rest of the way across. And the final result was that B went to C. Okay? And you just keep going like that. Where does Z go? Well, there's no Z, there's no Z, there's no Z. There's no Z until you get way over here to the left, and then Z goes back to A. Right? So there you go. Yeah. So every element of Sn can basically be broken down kind of like this. You just take every cycle that you see and you rewrite it using this little formula. Okay, and we're going to be doing this quite a bit today, actually, in this video. So it's worth making sure you understand this calculation. This is why I said that cycle notation, being able to work with cycles and multiply cycles is very important for this video. So if you need to pause and kind of take stock of how this is working, by all means feel free to do so. That's one of the advantages of a video, is you can stop and make sure that you're on top of this before we go any further. Okay, so hopefully so far so good. Keep in mind that the order of this cycle is still the length of this cycle. That little fact about using the LCMs of the cycles only works for disjoint cycles. So when you look on the right-hand side over here, you might be thinking, well, wait a minute, every cycle has length 2. The LCM of all of those 2's should just be 2. But no, these cycles are not disjoint, right? They're not disjoint, and therefore I'm not prepared to figure out the order of this element from looking at it on the right-hand side. I have to first simplify it, which is what we have on the left side, and then I see, okay, the length of that one single cycle is the order of that element. That's what you kind of have to go with. Okay. So let me just give you an example of this theorem. Let's suppose that I took something like 1, 8, 2, 6, and I wanted to multiply it by 3, 4, 7. Now this is a perfectly good element of, let's say, S8, and it's even simplified, right? When I say it's simplified, what I mean is that these cycles are disjoint. There are no common elements, no common numbers in the two separate cycles. So I have a 4 cycle and a 3 cycle. They're disjoint. So for example, the order of this element would be the LCM of 4 and 3, which is 12. So this is an element of order 12 right here. Okay? But let me not focus on that for the moment. I want to focus on writing it as a product of transpositions. Right? So using my little equation here that I've got, I'm going to put a box around it because we're going to use it right now. I can decompose each of these cycles. Like this first cycle, I could write this one as, how would it look? It would be 1, 6, and then 1, 2, and then 1, 8. Right? That's just for the first part. This is a cycle of length 4. I'm breaking it down like this. And for the second part, I can take 3, 4, 7, and I can write that as 3, 7, and 3, 4. Okay? So that's a perfectly good way to do this. Now, on the other hand, I want to point out, maybe I'll save myself a little bit of space here, that this element that I was working with, I could just as well write it slightly differently. I could write this element as 2, 6, 1, 8, and 4, 7, 3, right? I could do that if I wanted to. Actually, let me leave the second part the same as it was before. I'm just going to change just the first part. So suppose I take 2, 6, 1, 8, and 3, 4, 7. First of all, make sure that you agree that 2, 6, 1, 8 as a cycle is the same exact cycle as 1, 8, 2, 6. Right? 1 goes to 8, 8 goes to 2, 2 goes to 6, and 6 goes to 1. Right? It's the same exact thing that's happening here, right? 1 is going to 8, 8 back to 2, 2 to 6, 6 to 1. It's the same element, just with the numbers in a different order to start with. But if I took this and I wrote down the cycle notation in terms of the transpositions, right? As a product of transpositions using my formula in the box, well, what would I come up with? I would come up with 2, 8, 2, 1, 2, 6, and then, of course, 3, 7, and 3, 4. Okay? That is not the same as the product of transpositions that we saw on the left side in black. Right? There is a lack of uniqueness here. When we say that every sigma can be written as a product of transpositions, it does not say that it can be uniquely written as a product of transpositions. I mean, heck, I could come over here, I could take this expression, right, and I could just add a 4, 5, 4, 5 here, for all I care, right? This is just an element of order 2, so I really just multiplied by e, right? And this is still a representation of the same sigma as a product of, well, now 2 additional transpositions. Okay, so there's no uniqueness to this. I'm going to go ahead and erase my S4 here for now. We'll come back. I'll probably have to write it back up on the board again in a little bit. There's no uniqueness to this expression of sigma as a product of transpositions. However, there is something about this product of transpositions that is special. And this is going to lead us towards understanding what this alternating group is. Let me put a definition over here for you. And this is going to be the basis for creating this alternating group. So here's my definition. Let sigma be an element of Sn. Okay? We say sigma is even. Okay? Sigma is an even permutation, right? If it can be expressed, as a product of an even number of transpositions. An even number, now that could be 0, 2, 4, 6, 8, 10, 12, right? An even number of transpositions. Otherwise, sigma is odd. Well, that right there tells you that every permutation is either even or odd, right? Depending on whether you're expressing sigma as a product of an even number of transpositions or an odd number of transpositions. Okay. Now you might be a little nervous about this at this point, because didn't I just say that there's no uniqueness to writing sigma as a product of transpositions? It's not necessarily unique. Like what I did here, I added 4, 5, 4, 5, right? The original sigma right here, let's take a look at this original sigma. There were 1, 2, 3, 4, 5 transpositions. So this would have been an odd number of transpositions. After I added the 4, 5, 4, 5, now the number of transpositions went up to 7, which is actually still odd. Huh, that's interesting. There might be many ways to write our element as a product of transpositions, and even the number of transpositions might not be unique, but it seems to be, at least for this brief little moment, that if you finagle it in different ways, finagle, is that a word? If you write sigma in various different ways as products of transpositions, you're going to get a lot of different ways of doing that, but they're all going to be using the same parity of transpositions. Parity just means evenness or oddness, right? So either 5 or 7. I mean, we can do more things here. Now we have 9 transpositions making up sigma, right? But it turns out, it's not something I'm going to prove right now, but this is a fact, and the fact is that every sigma in Sn is either even or odd, but not both. It cannot be both. You cannot find one way of writing sigma using an even number of transpositions and then somehow another way of doing it with an odd number of transpositions. It's never going to happen. It's not totally obvious, for sure. I totally agree that it's not obvious, but it is true. And I'm asking you to take my word for that for now. Okay. So there's another fact. The second fact here is a little bit less cryptic. It's going to be a little bit more obvious, but it is a little bit weird at the same time. If we take a single cycle, right, of even length, and I'll illustrate this in just a second, okay? A cycle of even length is odd as a permutation, and a cycle of odd length is even. Oh boy. That seems a little bit unsatisfying, the potential to be confusing. But it turns out that when we talk about evenness and oddness, we want to be, as a permutation, we want to be counting transpositions, not looking at the length of the cycle. So let me just show this to you with an example. I think it should be very clear, right? So for example, if I take the cycle 1, 2, 3, 4, that cycle, of course, has even length, has length 4, but when I go through my procedure here of writing it as a product of transpositions, I'm going to write 1, 4, 1, 3, 1, 2, and there are 3 transpositions there, right, which is an odd number. So this is an odd number of transpositions. So a cycle of even length is odd with respect to this definition. It's an odd permutation. Okay? And similarly, if I took 1, 2, 3, 4, 5, which has odd length, well, I can write that as 1, 5, 1, 4, 1, 3, and 1, 2. And this is, of course, now exactly the reverse. This is an even number of transpositions. Oh boy. Okay? So whether we're counting the transpositions or whether we're looking at the length of the cycle, we sort of get the opposite answers. Okay? So that's a little bit crazy. But hopefully believable, right? A cycle of even length is odd with respect to this definition, and a cycle of odd length is even. Now, when we multiply permutations together, right? When we take a sigma and we multiply it by a tau, what do, right? Well, let's suppose that sigma is, I don't know, 1, 2, 6, 4, 3, and tau is, 2, 4, 5. And I suppose I want to multiply these together. Well, if I'm multiplying them together, I just set them side by side. Right? I just set them side by side. And what you might notice, for example, in this case, look at sigma. If I wrote sigma in terms of transpositions, it would be 1, 3, 1, 4, 1, 6, and 1, 2. That's sigma. Okay? And then tau would be 2, 5, 2, 4. This is an even number of transpositions. Makes sense because sigma had odd length. And tau also has odd length, and that's an even number of transpositions as well, right? We have 4 transpositions and 2 transpositions. So when you smash them together as a multiplication, or what we call composition, right? How many transpositions do we end up with here? Well, we end up with 6. 4 transpositions in sigma, 2 transpositions in tau, for a total of 6, which is still even. It's because when you add an even number to an even number, you get another even number. So somehow this evenness of our permutations seems to be closed under multiplication. If I multiply 2 even permutations together, which is what I did here, I get just a longer number of transpositions, but it's still an even number. Now the same thing wouldn't work for odd permutations. Okay? If I take 5 transpositions and multiply that by 7 transpositions, that's an odd number composed with an odd number, and I write them all down side by side, my full expression would have, well, 5 plus 7 is 12. There would be 12 transpositions, and that's not an odd number anymore. And that's because odd plus odd is not odd. So the odd transpositions don't seem to sort of be closed under multiplication, but the even ones do. And I bet you know where I'm going with this. Where I'm going with this is that if we gather up all of the even permutations, it turns out that we get a group structure. We get a subgroup of Sn. And that's what the alternating group is. Let me write it down, okay? Definition here. Okay. This is really cool. Okay, we have a subgroup now. The collection of all even permutations of Sn forms a subgroup. That subgroup is written A sub n, and it's called the alternating group. And it's one of my favorites. It's the alternating group. And it consists of all of the even permutations. By the way, is this thing going to be closed under inverses? Here's sigma, right? It's an odd length cycle, which means it's an even permutation, right? This backwards even oddness thing. This is an even permutation. But you see the inverse of sigma is also a 5 cycle, right? It has the same cycle type. The inverse of any particular element of Sn is going to be another element of Sn that has the same cycle type. Another great reason to want to use cycle notation. The inverses have the same structure, the same type of notation, or same cycle structure, I should say, right? And so if the inverse of sigma is also a 5 cycle, then the inverse of sigma is also even, right? If that's all we're doing is counting the lengths of the cycles and turning them into transpositions, it's going to be the same whether I use sigma or sigma inverse. All right. So this is a group. This is a group. The identity element, by the way, has an even number of transpositions in it, right? And you could actually think of the identity element as just 0 transpositions, right? There's nothing being transposed at all there. It's a completely trivial element. All right. So this is a subgroup of the whole group. Let me go back to S4 again, which is where we started this video. And what I'm going to do is I'm going to look at those 24 elements of S4, and I'm going to figure out which of them are actually part of the subgroup A4. Okay? I'm going to do that in the next part of this video. So I'm going to stop the current video. Be sure to watch the next part of it, which is going to contain that information as well as a lot more information about the alternating group. You're going to want to stay tuned. I'll see you again real soon, guys. Thanks a lot.